Welcome to Statistical Computing. Today, we are going to explore a fundamental concept in C and C++ programming called operator precedence. If you have ever wondered how a computer decides which part of a complex mathematical equation to solve first, you are in the right place. Let us dive in and build your understanding from the ground up. Now that we have introduced our topic, imagine you are at a busy four-way traffic intersection with no traffic lights. If everyone tries to drive at exactly the same time, there will be a massive crash. To prevent this chaos, we have right-of-way rules, where ambulances go first, then main road cars, and so on. In programming, when you write a mathematical sentence with many symbols, the computer needs similar traffic rules. Operator precedence is simply the strict ranking system that tells the compiler which operator gets to do its job before the others, preventing completely incorrect answers. This traffic analogy brings us to the core concepts of precedence and associativity. Operator precedence is built into the language to determine the grouping of terms. It dictates which operator binds to its surrounding values, called operands, first. For example, multiplication groups its numbers together before addition does. However, precedence alone is not enough. What happens when two operators have the exact same rank? That is where associativity comes in. Associativity is the tiebreaker rule that tells the computer whether to read those operators from left to right or right to left, ensuring predictable evaluation across all computers. Now that we understand what precedence is, let us look at the actual hierarchy of operators. To fully master C and C++, you must know this ranking. At the very top, level 1, we have parentheses, array subscripts, and function calls. These always happen first. Next, at level 2 are unary operators, which work on a single value, like the increment operator. Below that, at levels 3 and 4, we find the standard arithmetic operators. Multiplication, division, and remainder take priority and are grouped before any addition or subtraction takes place. Moving down from the arithmetic operators, we reach the lower levels of our hierarchy. At levels 5 and 6, we find relational operators like greater than, followed immediately by equality checks. Further down at levels 7 and 8 are the logical AND, followed by the logical OR. Near the very bottom at level 9 is the ternary conditional operator. And finally, at level 10, we have the assignment operators. This comprehensive ranking ensures that math happens before comparisons, comparisons happen before logical combinations, and everything finishes by assigning the final result to a variable. While most of these levels follow a simple left-to-right reading order, there is a massive exception that catches many students off guard. The assignment operator, which is the equal sign used to store a value inside a variable, associates from right to left. If you write a chain of assignments, the computer starts at the far right side of the line and works its way backward to the left. This makes logical sense because you must figure out the final value on the right before you can possibly store it into the variables on the left. To see this exception in action, let us look at a chain assignment formula. Here we have the expression x equals y equals z equals 5. Conceptually, this is used to initialize multiple variables to the same value at once. Let us break down the symbols. The letters x, y, and z represent integer variables in memory that are waiting to receive a value. The equal sign is our assignment operator, which we just learned operates from right to left. Finally, the number 5 is the constant integer value that we want to store. If this operator worked from left to right, it would try to assign y to x before y even had a value. Before we move on, let us see this chain assignment solved step by step. We are given 3 variables and 3 assignment operators. Because assignment has right to left associativity, the computer first looks at the far right and assigns the value 5 to the variable z. Once z holds the value 5, that exact same value is passed to the left and assigned to y. Finally, the value now stored in y is passed to the left and assigned to x. Our final answer shows that all three variables successfully hold the value 5, proving why right-to-left evaluation is necessary here. Now that we have seen how associativity works, we must address a dangerous trap that even experienced programmers fall into. You must never confuse precedence with the actual order of evaluation. Precedence only dictates how terms are grouped together, but it does not guarantee the exact chronological order in which the processor calculates those groups. This becomes a critical hazard if you try to modify a variable more than once in the exact same expression. The C standard calls this undefined behavior. This means the language rules do not specify what should happen, and your program might give completely different answers or simply crash. This warning about evaluation order leads us to a comprehensive mixed expression formula. Here we have R equals 5 plus 2 times 3 is greater than 10. Conceptually, this expression checks if the sum of two numbers multiplied by a third is greater than a fourth number. Let us define our symbols. R is our final variable that will store the result. The plus and asterisk are our standard arithmetic operators for addition and multiplication. The greater than symbol is our relational operator. If we increase the numbers on the left side, the relational check is more likely to be true. Let us see how the computer groups this. Let us evaluate this mixed expression step by step to see what value gets stored in our final variable. We are given a mix of math and logic, and we need to find the final integer result. First, the computer scans the operators present: addition, multiplication, and greater than. According to our hierarchy, multiplication has a higher precedence than addition or relational operators, so the computer groups the 2 and the 3 together first. We then multiply 2 and 3 to get 6. This simplifies our expression, preparing us for the next phase of evaluation. Continuing from our multiplication step, we now look at the remaining operators. Our expression is now R equals 5 plus 6 is greater than 10. Addition has higher precedence than the relational operator, so the computer groups the 5 and the 6 together. Adding them gives us 11. Now only the greater than operator remains on the right side. The computer checks if 11 is strictly greater than 10. Since this is indeed true, the relational expression evaluates to the integer 1. Finally, the assignment operator stores this 1 into the variable R. Physically, a value of 1 means the logical condition was successfully met. To make this step-by-step process completely clear, let us look at a visual representation of how the compiler groups the expression. This is called an expression tree. Notice how the multiplication of 2 and 3 is at the very bottom of the tree. Because the computer must evaluate the bottom branches before it can move up to the addition, and finally up to the greater than comparison at the top. The tree structure perfectly enforces the rules of operator precedence. This visual tree perfectly enforces precedence, but it brings us back to our earlier warning about undefined behavior. Consider this dangerous formula: A equals I plus I post-increment. Here, a student is trying to be clever by adding the current value of I and the next value together in one line. Let us look at the symbols. A is our result variable. The letter I is an integer variable that appears twice. And the plus plus is the post-increment operator, which adds 1 to the variable. If I increases, we expect A to increase. But as we will see, precedence cannot save us here. Let us try to evaluate this increment expression to see why it fails. We want to add the current value of I to the post-incremented value. Precedence correctly tells us that the post-increment operator binds tightly to the second I, and the addition happens after. However, precedence only groups the terms. The C standard does not specify whether the left I is read before or after the right I is incremented. Because this chronological order of evaluation is unstated, the final value of A is completely unpredictable. This proves that precedence is about grouping, not the strict timeline of execution. Having seen both successful evaluations and undefined behavior, we must ask why mastering this matters. Understanding operator precedence is absolutely critical for writing software that actually works in the real world. From banking software calculating compound interest to video games computing physics trajectories, mathematical formulas are often long and complex. If you forget that logical AND has higher precedence than logical OR, you might accidentally grant access to the wrong user in a security system. By mastering these rules, programmers can write concise, accurate code without needing to wrap every single pair of numbers in parentheses, making code easier to maintain. This brings us to the end of our discussion. Let us review the key takeaways. First, operator precedence acts as the universal traffic controller, dictating which operators bind to their operands first. Second, associativity resolves ties between operators on the same level, and you must remember that assignment works right to left. Finally, never confuse precedent grouping with the actual chronological order of evaluation. Keep these rules in mind, and you will write predictable, bug-free programs. Great job covering this topic.